Welcome to Lecture 2.4, Undetermined Coefficients. I'm assuming at this point that you've seen all of this material before, and thus I'm going to move at a rather brisk pace in this lecture. If you haven't seen this before, then please review my lectures from my Intro ODEs course on solving first and second order inhomogeneous equations. It's my thought that the second time you see this, it'll be a lot more familiar, especially now that you've seen some linear algebra and you understand the structure of the solutions to these equations. And so the big picture and the big ideas are much clearer. Okay, let's get started. Recall the main theorem from the previous lecture, which shouldn't even have been new then. This says that the general solution to a first-order inhomogeneous ODE has the following form. It's the solution to the related homogeneous equation, that is, when you get rid of g of t, plus any particular solution that you can find to the original ODE. Now, the homogeneous equation has a one-parameter family of solutions. That's a one-dimensional vector space, so it's c1 y1 of t for some non-zero y1, and then we add any particular solution that we can find. So this has a structure of like a line through the origin. It's like a vector space shifted away from zero. Here's our first example. We saw something just like this last lecture. I think it had slightly different coefficients. So to solve this equation, y prime plus 2y equals 6, we first write the homogeneous equation. I'm going to write it like this. And you look at that and you say that yh of t equals c e to the minus 2t. We find any particular solution. Notice that a constant solution will work, because for any constant, this derivative is 0, and we can solve for y. So we get that yp of t equals 3, and we add these together, and we get that the general solution has the form yh of t plus yp of t equals c e to the minus 2t plus 3. So one way to think of this is that our particular solution was a 0th degree 0 polynomial, and we found a particular solution that was also a 0th degree polynomial. That's going to be a common theme. We are going to guess that there's a particular solution of the same form as the so-called forcing term, the inhomogeneous term, and we're going to plug it back in and solve for it. So one thing that we could have done here instead of this is we could have said, let's suppose we didn't know what the constant was. Let's guess that there's a constant solution that is a, and let's try to plug this back into here. So you plug this back in, well, yp prime equals 0. And so if we plug this back in, we get 0 plus 2a equals 6. And so a equals 3. There's our particular solution. Now we just did this in our head, but I'm showing it to you this way because this is how we are going to generalize it when we have degree d polynomials on the right-hand side. And that's what we'll do next. For all of these examples, I'm going to keep the homogeneous part the same and only vary the inhomogeneous part, which we often call the forcing term. Now I should say that for equations like this, in your Intro ODEs course, you probably learn to use integrating factor or variation of parameters. Those will still work, but more often than not, this undetermined coefficients method, which you learned for second order equations, because that's all that you could do for second order equations, I think is better. And I think it makes it more consistent to use the same method for first and second order, because then you realize that the structure of these solutions really are the same. They're just vector spaces shifted away from 0. Okay, so the homogeneous part is yh prime plus 2yh equals 0, and we know that the solution to that is ce to the minus 2t. Now the inhomogeneous part, this is a degree 2 polynomial. So we always guess that the particular solution has the same form as the inhomogeneous part. So that's going to be at squared plus bt plus c. So this is also a degree 2 polynomial. And the idea is that if we take this thing, we take a derivative of it and we add it to 2 times itself, in other words, we plug it into here, we're going to get a degree 2 polynomial. And we have, on the right-hand side, a degree 2 polynomial. I'll write this thing as 6t squared plus 0t plus 0. And now, if we want to set equal two degree 2 polynomials, we have to equate the terms of the t squared variable, or the t squared term, the t term, and the constant term. And fortunately, we have three unknowns, a, b, and c, so that should be a system of equations that we can solve. Okay, so let's do this. Again, I'm going to work rather quickly. The derivative of this yp prime of t is 2at plus b. So now we're going to plug this guy back into the left-hand side. So y prime plus 2y equals 6t squared. Let's do this. So y prime is 2at plus b. 2y is 2at squared plus bt plus c. And now we have 6 times t squared plus 0t plus 0. We don't need those terms, but I think it helps. So now the left-hand side, I'm going to write this as some number of t squareds plus some number of t's plus, let's do this, so some number of t squares plus some number of t's plus some constant term equals 6t squared plus 0t's plus 0. So what goes in here? So how many t squareds do we have on the left-hand side? Well, we have 2 times a, right? So I'm going to put 2a right there. How many t's do we have? We have 2a plus 2b. So we have 2a plus 2b. And then how many constants do we have? We have a b here, and we have a 2 times c here. So we have a b plus 2c. So now to set these things equal, we have to set if these two degree 2 polynomials are equal, then 2a has to be equal to 6. Because again, these are the t squared coefficients have to be equal. The t coefficients, this is 2a plus 2b, that has to be equal to 0. And the constant terms, b plus 2c, has to be equal to 0 on the right-hand side. So this gives us a system of equations. 2a equals 6. So we also have 2a plus 2b equals 0. So we set those two equal, we set these two equal, and now we're going to set these two equal. So that's b plus 2c equals 0. So we want to solve this, and so we get a equals 3. We're going to plug that into here. So plug that in, and we get 2 times 3 is 6 plus 2b equals 0. So we solve for b, and we get that b equals negative 3. And now we want to plug this into here, and we get negative 3 plus 2c equals 0. And we get c equals 3 halves. So now we found our particular solution. We have determined that yp of t is, again, this is at squared plus bt plus c. So that's 3, negative 3, and 3 halves. So that's 3t squared minus 3t plus 3 halves. And now our general solution is y of t equals the homogeneous part plus the particular solution. So that's going to be c e to the minus 2t plus 3t squared minus 3t plus 3 halves. So there is our general solution. Example 3, the same homogeneous part. So yh prime plus 2yh equals 0. So the homogeneous solution, or the solution to the homogeneous equation, is c e to the minus 2t. Now the forcing term is an exponential function, 6e to the 3t. And remember, our general rule of thumb is that we are going to look for a particular solution of the same form. So an exponential function a e to the 3t. We want to figure out what a is. Let's convince ourselves why this works first. So if the right-hand side is an exponential function, e to the 3t. If we take e to the 3t times some a and we plug it in the left-hand side, look what happens. The derivative, we get some number of e to the 3t's, and here we get some number of e to the 3t's. So if we set a to be just right, the scaling factor, then we can set however many e to the 3t's we have in the left-hand side equal to 6 e to the 3t's. So let's do this. So the derivative, y p prime of t equals 3a e to the 3t. Now let's plug this back in. So y prime plus 2y equals 6 e to the 3t. Y prime is 3a e to the 3t plus 2 times a e to the 3t equals 6 e to the 3t. So now if what can we do? The left-hand side is 5a e to the 3t, and the right-hand side is 6 e to the 3t. So if these things are equal, then 5a has to be equal to 6. So that means that a equals 6/5. So we have our particular solution. We have that yp of t is 6/5 e to the 3t. So that's 6/5 e to the 3t. So our general solution is going to be y of t equals yh of t plus yp of t equals c e to the minus 2t plus 6/5 e to the 3t. And there we go. Example 4. Same homogeneous part, yh prime plus 2yh equals 0. So the solution to the homogeneous part is c e to the minus 2t once again. Now look at the right-hand side. Again, we're going to use our rule of thumb and assume that there's a particular solution, yp of t, of the form a cosine of 3t. It's the same, in other words, the same form as the right-hand side. But before we plug this back in, let's think about what's going to happen if we do. So if we do this, let's take a derivative. Yp prime of t equals 3a sine of 3t, and then it has to be negative. And now if we plug this thing back in to the left-hand side, we're going to get a sine here and a cosine here, and there's no way that we can add up a sine and a cosine to get a cosine. So this isn't going to work. So even though we did the general rule of thumb, the particular solution is the same form as the right-hand side, it isn't quite right. So what we have to do is we have to write this as the right-hand side as 0 sine of 3t. Do you remember this? And we have to guess that the particular solution has the form a cosine plus b sine of 3t. Now let's take a derivative of this part. So this is plus 3b cosine of 3t. And now look what happens when we plug this into the left-hand side. Once again, the particular solution has the same form as the right-hand side. It's just we had to tweak that form a little bit to see the bigger picture. So now if we plug this beast into the left-hand side, we're going to get sines and cosines. We're going to get some number of sines and some number of cosines. And we have to set that equal to 6 cosines and 0 sines. And that's two things. And look, we have two unknowns, a and b. So this should work. So let's plug this back in and let's check. So y prime plus 2y equals 6 cosine of 3t plus 0 sine of 3t. So y prime is minus 3a sine of 3t plus 3b cosine of 3t. That's y prime. 2y is 2a cosine of 3t plus 2b sine of 3t. Now, let me just leave the right-hand side blank because I'll just do that. Let's simplify this a little bit. So let's group together the sines and cosines. So how many cosines of 3t do we have? And how many sines of 3t? So let's see. So how many cosines do we have? We have 3b and we have 2a. So I'm going to write that as 2a plus 3b. Now how many sines do we have? We have negative 3a and 2b. So I'm going to write that as negative 3a plus 2b. And we have to set this equal to 6 cosine of 3t plus 0 sine of 3t. So in other words, this thing, 2a plus 3b, has to be equal to 6, and negative 3a plus 2b has to be equal to 0. So this gives us a system of equations. I'm going to write the simplest one first, negative 3a plus 2b equals 0. And then I'm going to write 2a plus 3b equals 6. So let's do the first one of these first. So which one do we want to solve for, a or b? Let's solve for, let's see, so this is 2b equals 3a. So b equals 3 halves a. So let's plug 3 halves a into b. And so now we have 2a plus 3 times, making sure I did this right, times 3 halves a. And so what is this? This is 4 halves plus 9 halves a. I should have picked an easier example. So this is 13 halves a. This isn't that bad. So 13 halves a equals 6. So a equals 12 thirteenths. Okay. And now let's plug that guy into the first equation. So I'm going to use blue now. So this first equation says negative 3 times 12 thirteenths plus, how about this? How about if I plug it into this thing here? So 3a, so I'm going to make that positive 3a. I'm going to make this equals 2b. Equals 2b. So b, so let's divide both sides by 2, and then we have instead of a 3 times 12 divided by 13, we have a 3 times 6 divided by 13. So we have an 18 thirteenths. So we have an 18 thirteenths. Okay, so now our particular solution that we were looking for is equal to 12 thirteenths cosine of 3t plus 18 thirteenths sine of 3t. So our general solution is y of t equals yh of t plus yp of t, which is c e to the minus 2t plus plus 12 thirteenths cosine of 3t plus 18 thirteenths sine of 3t. And so there we go. Now, something, again, you probably learned this in your Intro to ODEs course using the integrating factor method. I'm not even sure that would have even worked because you would have had to integrate the integrating factor. Yeah, it would have worked. The integrating factor, if you remember this, if you don't, that's fine. You take this, it's e to the 2t, and you multiply the left and the right hand side by that. Then you have to integrate e to the 2t times cosine of 3t. And that's rather nasty because you got to integrate by parts twice, and etc. Of course, if you can use Wolfram Alpha or a computer, you could also have done that down here as well. So I think this, if you can, I like this method better. Because, again, it's consistent. It works for first order, for second order, or for nth order equations in general. Here's our fifth example. So as before, same homogeneous equation, yh prime plus 2yh equals 0. So yh of t equals c e to the minus 2t. And now the right-hand side, or the forcing term, is an exponential function. So what we do is as usual, we guess there's a particular solution of the form a e to the minus 2t. Now what's the problem with this? So if we take this and we try to plug it in the left-hand side, what's going to happen? Shall we do it? Let's do it so you can see what happened. If you don't see it, you'll see it very shortly. So the derivative is negative 2a e to the minus 2t. So now let's plug this into the left-hand side. And we get y prime is negative 2a e to the minus 2t plus 2 times y, that's this, 2a e to the minus 2t, and set that equal to 6 e to the minus 2t. Now, what's the problem? Well, look what happens here. This is equal to 0. And so now we have the problem situation where 0 equals 6 e to the minus 2t, and that's impossible. So why did this happen? Well, it happened because our forcing term, our inhomogeneous term, unfortunately solves the inhomogeneous, or the related homogeneous equation. So something like this is never, ever going to be a particular solution. This will never have the property that when you plug it in the left-hand side, you get 6e to the minus 2t. Why? Because when you plug it in the left-hand side, it's like this, you get 0. So what do you do here? This is the so-called problem case. I called it that above, anyways. So now let's do what we have done before. We assume that there's a particular solution of a slightly more complicated form, v of t times e to the minus 2t. So let's take the derivative of this, integration by parts. We get v prime e to the minus 2t minus 2v e to the minus 2t. And let's plug this thing into the left-hand side now. So we have y prime plus 2y equals 6 e to the minus 2t. If we do that, we get y prime is v prime e to the minus 2t minus 2v e to the minus 2t plus 2 times y, or yp, is v e to the minus 2t. And look what happens, and this always happens. If it doesn't, you've made a mistake. We have to set that equal to 6 e to the minus 2t. So now what do we have? So what does this tell us? Well, we can also divide through by e to the minus 2t, and we can get that v prime equals 6. Okay, so if v equals 6, then we integrate both sides, and we get that v equals 6t plus c, where c is anything. So let's make our lives easier. Let's pick c to be equal to 0. So now v of t equals 6t. And our particular solution up here is 6t e to the minus 2t. There we go. We found a particular solution. So now we're done. Now our solution is y of t equals yh of t plus yp of t, which is c e to the minus 2t plus 6t e to the minus 2t. Now what always tends to happen in these type of equations, when you have one of these so-called problem cases, they arise in double roots, and they arise when the forcing term solves the homogeneous equation, is that you want a solution. In this case, you want one of the form a t to the minus 2t, and it doesn't work. So what you end up doing is sticking a t in front. This thing always ends up having a t in front. That's what happened before when we had the repeated root case. So in some classes, they just tell you blindly, they say, oh, if this isn't going to work, so try something like this. Yp of t equals a t e to the minus 2t. Stick a t in front. That's the rule that you need to memorize. Plug it back in and find a. And if you do that, you'll get that a equals 6. I think that's sort of a cookbook thing. It's memorize this instead of understanding why it works. So this is the more general form that I think is just as easy. Take v. We don't know what this is. We know a constant doesn't work, so try something slightly more general, maybe a polynomial, and you do that, and yes, you get that any polynomial of the form 6t plus c will work. So might as well pick the easiest one. Let's see b0. Here is v of t, 6t, and there is our particular solution, 6t times e to the minus 2t. To summarize what we've been doing so far, this technique is called the method of undetermined coefficients because we guess that there's a particular solution of a certain form in terms of like a and b or a, b, and c. We plug it back in and we figure out what those unknown coefficients are. It works as long as we can, first of all, solve the homogeneous equation. If we can't do that, we're out of luck. And next, we need to be able to find a solution either by inspection or with an educated guess. If we can't do one, we're basically out of luck. I mean, if you can't solve the homogeneous equation, like if you separate variables and you can't compute the integral, well, there's nothing more you can do. If you can't do two, if you can't do things by inspection or by an educated guess, then there are two alternative methods. You can use the integrating factor method, or you can use variation of parameters. I'm not going to review these methods here. If you want a refresher, please go back to my Intro ODEs course. I think I have a whole lecture on each of them. Most of the time, you don't need these methods. Most of the time, it's easier to solve using the method that I've been doing all lecture, the undetermined coefficients. It's use an educated guess, plug it back in, and find the coefficients. Unfortunately, they don't really teach this in your standard ODEs course until you get to second order because, well, they have these cookbook methods that they don't really motivate too well, that don't work for higher order ODEs that they teach you, and then they do a 180 and show you this method of undetermined coefficients for second order, so it seems a little bit hodgepodge. And of course, you can find examples of ODEs where you can't guess and check a solution. One example is like y prime plus 2y equals tangent of t. Like you're not going to be able to find a particular solution such that when you take its derivative and then add to twice itself, it has the same form. Because tangent, when you take its derivative and you add it to twice itself, doesn't have that same form. So this guess and check is not going to work here. You have to use one of these guys. Of course, you can debate how realistic some of these equations actually are in practice, where you need these two methods. Finally, these two methods aren't guaranteed to work either. First of all, they work equally well, and both of them will. The hard part is when you get to this integral, e to the integral a of t times g of t. And recall, here we have y prime plus a of t y equals g of t. So if you can integrate this function, then you can use either of these methods. If you can't integrate it, maybe it's e to the sine times cosine of t or something weird like that, times who knows, then this method isn't going to work either. Now, I will say that these methods are equally hard. Like if one of them's tricky, the other one is going to be too. Both of them, the hardest part is this integral. However, variation of parameters has a built-in checkpoint. Go back to my Intro ODEs lectures if you want to check this out. And by that I mean you plug things in and things always massively cancel. And if they don't massively cancel, you know you've made a mistake. Stop, go back and try again. Integrating factor method doesn't have that checkpoint. If you mess up the integrating factor, sometimes by a negative sign or a constant, it's easy to do. You'll never know it. What you end up getting is not the solution, and you won't be able to catch yourself. That said, my experience, having graded thousands of exams, or at least hundreds, probably 1,000 now, is that most students prefer the integrating factor method, and I think the only reason is because it's usually taught first. instead of variation of parameters. So if you got to go one of these, I would recommend variation of parameters. Again, they're equally difficult or equally easy, depending on your view of life, but the variation of parameters has a built-in checkpoint. You will make fewer mistakes using this method. Next example, solve y prime plus 1 over ty equals 1. So, can we guess a particular solution here? I don't know, I can't. So I guess I lied when I said that I wouldn't go over the integrating factor or variation of parameters method. Well, I won't go over it very much. I'm just going to quickly do this problem both ways. So again, if you want details in this method, please see my intro ODEs lectures on them. So first, the integrating factor. Remember how to do this? So you always divide through, so the y prime term is monic, so that means the coefficient is 1, and then you circle this coefficient of y, and your integrating factor is e to the integral of that 1 over t dt, which in this case is e to the natural log of t. You don't need a constant here, and this of course is just t. So I really did make this as easy as possible, because usually you get something like e to the t squared or e to the sine or something nasty like that. Okay, so now what we do is we take this equation y prime plus 1 over ty equals 1, and we multiply the left and the right hand side by this integrating factor. So that usually it's an exponential function, but because I picked it so this would cancel, in this case it's just t. And the reason you do that is because now the left hand side is primed for the product rule in reverse. Remember that? So this is t, the integrating factor, times y prime. That always happens. That's why we choose this particular integrating factor. And you can check that the derivative of this is indeed that. And the right-hand side, of course, is just 1 times t, which is t. So now we can integrate both sides. And now we get t times y. The integral and derivative cancel each other out right here. So we get t times y equals 1/2 t squared plus c. And now we just have to divide both sides by t. And we get y equals 1/2 t plus c over t. So c times t to the minus 1. So this is our particular solution. Sorry, this is our general solution. And so what's the simplest solution here? So all of the solutions have this t inverse term except when c equals 0. So it turns out that if you had guessed that 1/2 t was a particular solution, well, then you could have skipped this step. But I don't look at this and say, obviously 1/2 t is the solution. Do you? Well, if you do, all the power to you. Okay, let's do the variation of parameters method. So for this one, so this is variation of parameters, just so we the homogeneous equation first. I'm going to drop the h here. I'm just going to write dy dt equals -1 over t times y. And now we want to separate variables. We get equals -1. Integrate both sides. We get natural log of y. And on the right hand side, we get negative natural log of t plus c. We integrate both sides. And now we get y equals, so remember we can always take this constant out in front, y equals c e to the natural log of t to the -1, which is c times t to the -1. That's the homogeneous solution, and yes, that is in fact what we got right here. So this actually is the homogeneous solution, and this is a particular solution. So now, the variation of parameters method. Remember what we do. So we assume that there is a solution. So next we assume that there is a solution of the form, the homogeneous solution times v of t. So we've actually done this before a little bit. V of t times t to the minus 1. And then we're going to plug that guy back into the original ODE and figure out what v has to be. So y prime equals v times, or v prime times 1 over t plus v times the derivative of t inverse. So what is that? That is negative t to the minus 2. And now we're going to plug this back into our ODE. So we're going to plug this back into y prime plus 1 over t times y equals 1. Okay, let's do it. So y prime, that's this guy. So that's v prime times 1 over t minus v times 1 over t squared. So that's v prime plus 1 over t times y. So that is plus 1 over t times y is this one. So this is v times 1 over t. And the right-hand side equals 1. So we have to somehow set this equal to 1. Is this really going to work? Well, I promise it is. So why does this work? So things will cancel. As I said, things always cancel. This is a nice peace of mind built-in checkpoint. That will cancel with that. You see that? So these things will cancel, and now we are left with that equaling that. So let me go up here, and let me write this as v prime equals t. Oh, look at that. It looked like it was going to get messy. So again, this is v prime over t equals 1, so v prime equals t. So that means that v equals 1/2 t squared plus c. And so our general solution here is v times t inverse. So that means that y of t equals v of t, which is 1/2 t squared plus c times t inverse, and that is exactly what we got right here. If we multiply this out, this is 1/2 t plus c t inverse. There is our other solution. So in this particular case, the integrating factor method actually was shorter than variation of parameters. But that's because we got really lucky. I specifically chose this knowing that the integrating factor method would be e to the natural log of t and would cancel out like crazy. So normally these are equally the same, and neither of these are too hard. If one of them works, the other one will work, and vice versa.
We've spent most of this lecture looking at first-order inhomogeneous ODEs and using the method of undetermined coefficients to solve them. We'll spend the rest of the time looking at second-order equations, and it basically works the same way. The general solution to the following inhomogeneous second-order ODE, as before, has the following form. It's a solution to the related homogeneous equation plus any particular solution that you can find. Only difference here now is that the homogeneous equation is a second-order equation, and so the solution space will be a two-dimensional vector space. So it's going to have the form c1y1 plus c2y2. We can verify this just like we did for the first-order case in the previous lecture, and I'll leave this as a homework exercise. To solve a second-order linear inhomogeneous ODE, the method is basically the same. We first solve the homogeneous equation, and then we find any particular solution, yp of t, to the original inhomogeneous equation, and then we add those together and we're done. The general solution is y of t equals yh of t plus yp of t, which is c1y1 of t plus c2y2 of t plus yp of t. We'll finish with 3 second-order examples, and again, I'm going to do these rather quickly. So all of these have the same homogeneous equation. So let's solve that one first. So let's right away write the characteristic equation. That's r squared plus 3r plus 2, which is r plus 1, r plus 2. I think this is the same example from the last time. So the homogeneous equation is c1 e to the minus t plus c2 e to the minus 2t. So I'm only going to write this down one time. Henceforth, I'm going to write yh, and that's what it is. So the first one, I've made this simple, so there's a constant solution. If there's a constant solution, that means that you can make the derivatives 0 and solve for y, and you get that yp of t equals 1/2. I made it so you can do it by inspection. Or you can just say this is a degree 0 polynomial. Guess it's of the form yp of t is a, plug a back in, and you'll get the same thing. So here, y of t equals the homogeneous equation, which is directly above, plus 1/2. Okay, next one. Now the forcing term is a degree 2 polynomial. So we have to guess, so for problem 2, we have to guess that yp of t equals at squared plus bt plus c. And you take a derivative, and you get 2at plus bt. You take a second derivative, forgot my prime there, and you get 2a. Now let's plug this guy in, and y double prime is 2a plus 3y prime, which is 2at plus bt plus 2 times y, so that's 2 times a t squared plus bt plus c equals 4, oops, not 4e, and not 4 either, it's negative 4. So that's negative 4 t squared plus 0t plus 0. So let's collect terms. So how many t squareds do we have? So I think we only have one, so that's a 2a t squared. So we have 2a times t squared plus, how many t's do we have? So we have 6a plus 2b. So we have 6a plus 2b. And then how many constant terms do we have? Well, we have a 2a, and then we have a 3b, and then we have a 2c. I'll make that black, and that's equal to negative 4t squared plus 0t plus 0. So we need to set 2a equal to negative 4. We need to set 6a plus 2b equal to 0. We need to set this creature equal to 0. So we get a system of equations. I'll do this one by one. So 2a equals negative 4. Before I even write the other two, I'll say that a equals negative 2. Now let's plug that into the second one. So we get 6 times negative 2, so that's negative 12 plus 2b equals 0. So 0, that tells us that b equals 6. And finally, the third one, so 2a, so that's that's negative 4 plus 3 times b, that's 6, so that's 18 plus 2c equals 0. So this is 14, so we get that c equals 7. So now we have our particular solution. It's a polynomial of degree 2 with coefficients negative 2, 6, and 7. So our general solution is the homogeneous solution plus negative 2t squared plus 6t plus 7. There's our second one. Now for our third equation, our forcing term is this exponential. So we are going to assume, as before, that our particular solution has that same form. So it is of the form a e to the 3t. So let's take two derivatives. Y prime equals 3a e to the 3t, and y double prime p is 9a e to the 3t. And now we're going to plug this in. So this is number 3. So y double prime is this guy. So that's 9a e to the 3t plus 3y prime. That's this one, 3 times 3a e to the 3t, plus 2 times y, which is a e to the 3t, equals 4 e to the 3t. So we have e to the 3t's everywhere, so how many e to the 3t's do we have on the left-hand side? Well, we have 9 plus 9, that's 18, 19, 20a, so we have 20a e to the 3t equals 4 e to the 3t on the right-hand side. So we have to set 20a equal to 4, and we get that a equals 4 over 20, which is 1/5. So our particular solution is 1/5 e to the 3t. So our general solution is the homogeneous equation, which again is above, circled in red, plus 1/5 e to the 3t.